Well, sorry for this bad introduction, but good evening, everyone. This is Celso Batalha, Astro 10 online, and so today I would like to start with a question asked by a student, and the question is right here. So, in this picture, you have the sun in the center, and you have a orbit describing Earth position in different months. By the way, somebody has the microphone on. Can you turn it off? It's giving some background noise. And you also have in the sky the constellations of zodiac, and then you have Taurus, Aries, Pisces, and I think I in one of the previous chat room I tried to make sure these constellations were positioned properly, but they were not. So one of them is off a little bit, but this does not um, prevent us from answer the question that is asked here. So assume that you are observing the night sky from a typical city in the United States, latitude plus 40 degrees. So basically what's saying here is imagine that you're living in the northern hemisphere. And the reason is if you are not, if you are in the southern hemisphere, the sky will be switched in the way we see things in the sky. Moon's phases, as I commented yesterday. So use the figure below to determine which constellations of the zodiac would be rising at 10 p.m. Would be rising at 10 p.m. In May. So what we need to do is to take Earth, which is right here, right, and place Earth in the month of May. So month of May is right here, right? Uh, yes, very good. Thank you. You're saying that your microphone was giving some 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 background sound. But anyway, so if you place Earth, let's see if I can bring a whiteboard. So then we have the sun right here, right? And the month of May, let's place Earth right here. I can't draw that well, but we have something that's more or less like this. And here's the month of May. So at midnight in the month of May, if you look up to the sky at midnight, which means directly opposed to the sun, you see this constellation that happened to be here, and that is, which one is that? Scorpio? No. Yeah, Scorpio. Doesn't look like Scorpio. So we have a Scorpio. Yeah, so Scorpio right there at midnight, right? Midnight. So Earth rotates in the sky, as seen from north perspective, counterclockwise. And this type of motion is called prograde, which is part of the discussion that goes in this week, prograde motion. So Earth also spins in the space around its axis of rotation counterclockwise. Why is that? Because not only planet Earth, in fact the sun, if you place a axis of rotation in the sun also rotates around its own axis of rotation counterclockwise. And the reason to that is the sun and the planets and the satellites, they all came from a same cloud that were rotating in that direction. I seen from the north celestial perspective, um, not including or considering collisions that might have happened in the very beginning of solar system. um, all objects should be in that particular orientation or orbiting that particular orientation. Major exceptions are moons around Jupiter and Saturn. Some of them are captured, and then you have some different history going on there. But basically, so Earth at midnight, somebody at midnight should be facing the constellation Scorpio. So midnight, noon is right here. This is noon. So at noon, somebody on Earth is pretty much facing the sun, which means 9 p.m., that person here in May should be facing, I don't know, more or less. So if you draw a tangent here at 9 p.m., should be hitting this constellation, which is Virgo. So 10 p.m. should be in Virgo. So I would mark Virgo. Anika, does that make sense? Especially based on what we saw yesterday in the chat room?
I don't understand how you know exactly where to stop.
Where to stop what?
Like, how did you determine it was Virgo?
So can you see that at noon on May, some person on Earth, let me make a bigger Earth, just a second. Where's my eraser? Do I have an eraser here? I should have an eraser. There you go. Make a better drawing. So let's start with the sun. And what I would do, I would place Earth in a better position so that you can at least understand the idea. So I'm going to put Earth in the month, according to the figure right here, the month of August. So right there. And Earth has this, this is the North Pole. And let's put the clock on Earth like we did yesterday. So if we put a clock, this position here on Earth should be noon. And since Earth rotates counterclockwise, I see from somebody in the north part of the sky. So this is pretty much the line connect Earth to the sun. So this is noon. Midnight is somewhere here. So midnight. And so the middle of noon and midnight is 6 p.m. So 6 p.m. is somewhere here. And between 6 p.m. and midnight is the time 9 p.m. So let's translate that in this drawing. So can you get these times? Okay.
Yeah, I get that.
Okay.
And we know that it's the north because they said that it was latitude 40 degrees.
Yes, at
okay.
40 degrees north, correct.
Okay, yeah,
absolutely. So at 9 p.m., this person here on Earth is looking basically not at a line perpendicular to the line connecting the sun and Earth, which would be this line over here. In fact, I think I made a mistake. It's not Virgo. So let's say this is noon, midnight up there. So 6 p.m. would be Sagittarius. So between 6 p.m. with Sagittarius and midnight, which is probably Aquarius, the constellation in the sky would be Capricorn, if we were talking about August. So in May, Earth in May, and that's the exercise, at noon, you are facing the sun. Midnight, you face Scorpios. Between noon and midnight, 6 p.m., you would be facing a region that is pretty much tangent to the circle. And I don't know, it seems to be falling probably in Leo. So if you take a tangent on May, it's going to fall on Leo. And that is 6 p.m., right? That's the region here, 6 p.m., which is perpendicular to noon and midnight. So you have the orbital circle going like this, right? And then you are taking a perpendicular at 6 p.m. that's falling in Leo. So between 6 and midnight, which means between Leo and Scorpio, I have two constellations, Virgo and Libra. So I would take 9 somewhere in the middle. That would be Virgo. That would be my take. But again, this is too demanding, and these constellations are not pretty much okay. We could make a check. So if we want to do a cheating thing, so we go to the month of May, and we go at 10 p.m. And with constellations of zodiac, we would be seeing up in the sky. How do we do that? View, constellations, labels, illustrations. No, I don't want that, sorry. View constellations, I don't want illustrations. View constellations, I want a zodiac. And high up in the sky would be this one over here. What's the name of it? Label, label, label. Constellations. Yeah, Virgo. I mean, that's the idea. But again, for the midterm on Thursday, if you could fix more on the moon's phase and those questions we discussed yesterday, that would be great.
Okay, thank you. That helped a lot. I understand.
Okay. All right. Good. It's not. I mean, it's a lot of abstraction, and you have to see circles, and it's not obvious. So what I would like to talk about today is, in fact, I would like to start talking about is prograde and retrograde type of motion, what exactly that is. So we saw previously that one of the major motion that Earth goes through is Earth rotation on its axis of rotation. And we see this type of things in the sky. See, the time is running quickly, right? We are in the northern hemisphere, and then we see the constellations and the stars and the planets. Let me see if I label the planets too. There you go. So we have the planets and the constellations of zodiac. They all rise in the eastern sky, and the sun is going to come up quickly, right? And then eventually they set in the western sky. And the reason of this so-called daily or diurnal motion is because our planet Earth itself is spin in space from the western sky, which means right here. So Earth is going from the western sky towards the eastern sky. So instead of seeing stars rising, what we really should see is Earth in this horizon over here going down in the sky. I don't know if you could make that abstraction. So you don't have the sky kind of a rising up as we see it, but in reality, let me get rid of daylight. But in reality, what we do have is Earth going down in the eastern sky, because Earth rotates or spins in the space from west to east. So again, instead of seeing the sun going down in the western sky, we should develop the capability of abstraction and in fact see the Earth in the western sky going up, right? going up towards the sky, if you imagine Earth to be a big sphere out there. So what I'm going to do now is to stop this Earth rotation and let me focus on one particular constellation, like Scorpio. So imagine we have the ability of take a spaceship or a rocket. So let's take a rocket and go up in the sky like this. So we are blasting off, and we are in the same location, except that we are, so you can see Earth down there. See that? Earth is there. We are in space. Make sure you have your space suit. So we are up in space, and what I'm gonna do is to do a little trick. And the trick is I will not be bound by Earth rotation. So Earth down there, so we are in space, so Earth down here is rotating, spinning, like we all know. And that process of rising and setting will continue for somebody on Earth, but the trick that I'm going to do now is pretty much go up in space and be staring at Scorpio all the time. Because let's say I love Scorpio. It's great, it's a beautiful, gorgeous constellation. And in fact, it is. It's a beautiful display of sky, of stars. So if I do that, I could speed up the time. If I could, so that I close my eyes and I open again in about 24 hours. In fact, it's not exactly 24 hours. It's one sidereal day. It's a trick that the software has to enable us to keep staring at the same region in the sky always and not spinning along with Earth. Okay, so Earth is down there. If you could look down, Earth would be spinning in the way it always do, but we are not rotating along with Earth. If I do this, look what happened. See that? So the moon, which we saw previously in the previous exercise of daily or diurnal motion, the moon and the stars and the planets were all slowly rising in the eastern sky and then going all the way to the western sky. This is not happening anymore. So the moon is going slowly but surely towards the eastern sky, which means every day, if you keep staring at the same sky region, you see the moon passing from your right hand side to your left hand side. And again, we call this type of motion prograde motion. Okay. Now, if you keep doing that, look of what happened with Jupiter here. Jupiter is every day is going a little bit to the west in respect to the stars. So in respect to there comes the moon again. Yeah, the moon is coming again in its path from west to east. So in fact, we just passed Earth's shadow. See Earth's shadow right there. So if the moon had gone through Earth's shadow, we would have an eclipse. So, but it didn't. So if you look, and I will speed this up. And now Jupiter also is going from west to east. The sun is going from west to east. So what you're seeing here is the following. Planets, and that includes the moon and include the asteroids. As you can see, there is Ceres, which is a dwarf planet now. You see Mercury. So planets, the sun and the moon, they have some independent apparent, because it's not a real motion we are seeing here. We are seeing an apparent motion in respect to the stars in the background. The stars seems to be fixed. The stars are so far away, they seem to be fixed. But in respect to the stars, the planets, the sun, and the moon, they seem to be moving from the western sky all the way to the eastern sky most of the time. In fact, the moon and the sun, they always go from west to east in respect to the stars in the background. And this type of motion is called prograde motion. Prograde motion. Now, retrograde motion is the contrary. Is what Mercury just did here. So Mercury goes prograding and will start retrograding, like right there. See, this retrograde motion is the apparent motion of planets in respect to the stars in the background, in which it appears that goes from east to west in respect to the stars. So that's it. Think about prograde and retrograde motion. This is what it is. Look at Mars. Mars is prograding. Mars is prograding right here. Keeps prograding, keeps prograding, keeps prograding, and progrades all the way. Let me see another planet. Look at this dwarf planet. Make is retrograding. Let's look at Venus. Venus prograde, 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 and retrogrades. And progrades again, progrades, 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 and keep prograding, but eventually will retrograde. So how to explain that? Look at Mars. Mars is prograding, 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 prograding all the time, but eventually might retrograde. Jupiter is retrograding, so it's going from east to west in respect to the stars. So once we identify this type of motion in ancient times, so if you go several thousands of years from now, 3,000 or 4,000 years, they were observing and finding out planets. In fact, more than 7,000 years. In fact, the word planet it's called the wonders, because the planets in respect to the stars. I mean, for all purposes, you look up to the sky. Planets look like a star. It's bright. Some planets are faint, like Pluto. Pluto is faint, right? So barely can see it. But Pluto is not a planet; it's a dwarf planet. But although they appear like a star, they have some intrinsic motion the stars don't have, right? So the stars, which now we know they are far away, the stars, they seem to be, their relative position seems to be always the same. They do move, but they are so far away that their relative spread or conglomerates or getting together in space, we don't see it because they are so far away. Why do we see planets doing this type of motion? That was the major task that astronomers in ancient times took to explain. So the first explanation we have was given by Ptolemy. In fact, several, as far as mathematics is concerned, Ptolemy gave the first worldview that explained that. And I will show you here. I think software has this type of things. No. Just a second. I have to find Earth, sky, blank, blank, blank. No, solar system, Earth, eclipse, inner planet. Okay, Mars retrograde now, inner solar system, eclipse, Venus, moon, other planets. No. Space station, Russia. For historical dog days. No. Star, no. Deep space, no. Exoplanet, no. Well, where is it? I don't know what it is. That's not good. Is no, it's not here. Just a second. Solar system, meteorological space mission, all opinion. There's no favorite. It's not showing. That's so bad. That's not Mars Express. New Pioneer Guides. Session, solar system. Because I'm using a new edition of the software and they put it in a different place. What I'm trying to find is a description of the planetary motion in geocentric worldview. Man, I can't find it. I do a geocentric. Let me see, geocentric. Yeah, it's not showing. Sorry, I should have get this before. Yeah, but I can show maybe on my favorite in the solar system. I can go to inner planet, inner solar system. Oh, it's right there. I found it. Okay, let's see solar system. There you go. Earth-centric. So in the Earth-centric worldview, so Earth is not moving, and this is how the ancient observer interpret prograde and retrograde motion. So the sun, in this worldview, if you map the position of stars and the position of the planets, you can, for instance, we think the sun in respect to the stars move from the western sky to the eastern sky always prograde. See, the sun always prograde. Same thing with the moon. The moon is not showing here, at least I don't see it. Now let's take a look at Venus. Venus is prograding now, but then eventually we'll get to a point that will start retrograding, and it's going to happen now. And retrograde, see that? So in respect to the stars, Venus seems to go backward and then do a little dance and then it keeps prograding again. So again, if you take the position of planets in the sky and the stars and map that properly, you can create a worldview that is called geocentric, Earth in the center, and you can predict planets' position. Why was this so important? And they put so much mathematics on it because of astrology. In the beginning of the first century, astrology was important for the kings and to make predictions about business and wars and things like that. They thought the planets were some sort of a living gods, and to predict where the planets would be, let's say months or years from now, and if the planet would be prograde or retrograde. If progrades, it means some things. Retrograde, they would ascribe some different interpretation. So the mathematical model to predict position was very important for astrological purposes. So this is the geocentric worldview, and Ptolemy was the mathematic astronomer who developed this model. Now, in this model, the planet does not orbit Earth. In fact, the planet orbits a circle called deferent, and this deferent itself is the one that goes around Earth. Now, the other worldview is the geocentric worldview. And the geocentric worldview, the heliocentric worldview is the one that Helios, the sun, is in the center. So this type of model was championed by Copernicus, in which he forced the planets go in a circle. Why circle? Because circle, in fact, gives almost a good result, but not exactly perfect. And circle was also considered a sacred symbol in those days. And these planets, again, were associated with gods, with perfections, with absolute things. And so they should go about their own business in a circular fashion. But Mars was not fitting well. In fact, very few planets would be predicted properly with the heliocentric worldview presented by Copernicus. And this was solved later on. This is the inner solar system. I can show you the outer solar system. They also go in a circular fashion. There you go. And now you have the major Galilean planets or gas-like planets going around the sun. They all go in the same direction, counterclockwise, and we call prograde type of motion. My battery is dying, so I have to get just a second. Let me get alive. I need to give some juice to my computer. There you go.
Alert from System UI server.
I know.
Low battery.
I know. Thank you. All right. Okay, so heliocentric worldview, Helios, the sun in the center. Geocentric worldview is Earth in the center. Now, Kepler came later, and Kepler was able to. There is a background noise going on. Is this me?
Put it away. Oh, you do?
Is somebody with the microphone on? No?
Your phone. Why are you recording voices? Hello?
Just a second. There is some interference here. Can you guys hear me now? It's okay? Okay. So Kepler came after Ptolemy, Copernicus, and using primarily data collected by Tycho Brahe. And if you go to your book, there's a nice introduction to Tycho Brahe, one of the great observers of all times. And he had his own observatory, and he was able to use all these instruments to mark position of planets with very good precision according to those days. And by doing so, it was found that neither Ptolemy or Copernicus circular orbit or elliptical type of orbit would match the observations. And just to make a long story short, Johann Kepler was able to explain the motion by placing the planets going around the sun, not in a circle, like this example here, but in an ellipse type or elliptical type of orbit. So an ellipse is a curve that you can draw quite easily if you have a thumb tag, two thumb tags, and then you make a string. You make a string be around these thumb tags, and then with a pencil you just draw this curve. So there is a mathematical way to explain or to predict these points in the circle, but we don't care so much for that. So an ellipse has a semi-major axis, which is this distance over here, and semi-minor axis, which is the smaller distance. So ellipse is a little bit flattened, as you see. So the semi-major is bigger than semi-minor, or the major axis is bigger than the minor axis. It was found the planets obeyed this orbit quite well. And later on, Newton came and using this law of gravitation, which comes after here, was able to nicely explain why the orbit should be an elliptical orbit and not a circle. So the first law of Kepler is that orbital path of planets around the Sun describe an ellipse, and the Sun happened to be in one of these thumb tags, and they are called focus. So there are two foci in an elliptical orbit. So the Sun is in one of it, there is nothing in the other one. So it so happened the planets, they go around the Sun in an elliptical path that is not so eccentric, and we call eccentricity is when this curve is very flat. So for instance, a circle is a particular case of an ellipse that this eccentricity is zero. So there is not eccentric. The two axes, the major and minor axes, have the same size. Is the diameter of a circle. So the second law of Kepler is also sometimes called the law of equal areas. So if you look at A and B, and if you are able to calculate the areas, and now you have to go back to your high school when you studied geometry. Who studied geometry before? It was so many years ago for some of us. So, yeah, it's funny, huh? So if you look at areas like area of a square of size A, so it's A square. But it so happened in this elliptical path, you have a complicated way of calculating areas because it's not a square or it's not a rectangle, it's a curve. And to calculate that, a new mathematical formalism had to be developed. In fact, Newton was the one who developed that to calculate this area. So if you manage to calculate area A and B and find they are the same, there is some astronomical phenomenon associated with that. And that is the time it takes the planet to go from point 3 to point 4 equal the time the planet go from point 1 to point 2. In other words, if you draw a line that comes out of the Sun out to the curve and take this line and force it to sweep an area that is equal to B, the time it takes to go from, let's say, point 2 to this new point representing in the same area should be the same. So what is the consequence of this second law of Kepler? And again, later on, Newton was able to explain why this is the way it happens, the way it is so happened. The consequence is when the planet is further out of the Sun in what's called the aphelion part, the planet goes slower, the speed is less, or the average speed is less than it is when the planet is closer to the Sun. The planet speeds up because it has to cover a longer path in the same amount of time. So the planet speeds up closer to the Sun, and then it slows down as it goes away, and then it starts speeding up again, reaching higher speed when it's closer to the Sun. Okay? That's the second law of Kepler. And the third law of Kepler is more a mathematical law that says P2 is equal A3. P is the sidereal period in units of solar Earth, in fact, years. So what is this ideal period of our planets? Is the time it takes the planet to complete a orbital turn around the sun. So all the planets obey this orbit quite well. You take the period, so the time take the planet to revolve around the sun in Earth years, and then you square that. You found the number is pretty much equal to the semi-major axis, which means the average distance between the planets and the sun, uh, close to that because it's an elliptical, to the third power. That is the third law of Kepler. P2 is equal A3. And I recommend that you review these laws as we move on. Now, this is important because Newton's law, in fact, Newton's law of motion, usually I don't go there. I don't cover this part, although if you want to read is important because it has a lot of physics, and if you want to learn this with more detail, go to my physics class and then we can play in there. I will go back to some of these concepts when we start stellar evolution. When a star forms because of these physical terms like angular momentum, and so the star has a tendency of spinning up as gas contracts and form a star. But for now, I want to focus on this, the universal law of gravitation. And this was one of the most intuitive and greatest vision of Newton, Isaac Newton, 1700, and that is the force that attracts Earth to the moon is given by a constant multiplied by the mass of Earth, mass of the moon, divided by the square of distance between Earth and the moon. And gravity force is operating everywhere as long as there is mass involved. For instance, if you take the mass of your body, it's about 60 or 70 kilograms, something like that, and you multiply the mass by the mass of, let's say, mass of Earth, and take the distance of where you are to the center of Earth and square, multiply by this constant, you have a force that is called your weight. Your weight in pounds, how many pounds you have, is equal to the product of this quantity here. And that is quite amazing. And this is extended out not just between Earth and the moon, but also Earth and the sun, and to the entire galaxy. So when you look at a galaxy with 300 billion stars, so all these stars, they have their own mass, and this mass interact with one another, attracting as the result of what we call gravity. So gravitational force is a force important because it's one that tries to bring things in, try to bring masses together. And for instance, we walk and we are stuck to the floor, and if we jump, we fall back because Earth attracts us with its own mass. Now, if we were in a planet that had less mass, so if we jump, we would probably jump much higher than we do on Earth if we were in a planet of less mass. By the same token, if we were on the surface of a rocky planet that is more massive than Earth, when we jump, we wouldn't jump as high, or perhaps we wouldn't even able to get off the floor because the attraction, the gravity force connecting, gluing us to the floor would be paramount. So gravity force is fundamental, is everywhere. When you launch a rocket, you have to be able to overcome, to give enough fuel to the rocket so that it can overcome the gravitational pull of Earth, so that everything that comes out of Earth has to go back. Unless you shout you shoot this rocket with a speed that's called escape velocity, in which this object will not come back, is able to overcome this gravitational force. So yes, this equation here is very important, and it's gonna be following us throughout this course. I would like to finalize today reminding you of our upcoming exam on Thursday, and also to let you know that I would recommend review the moon's phase and that trick I gave you to determine at what time certain moon phases are supposed to rise and set. I also would recommend that you go to the end of chapters and don't worry about mathematics. It's not going to have a mathematics equations in there for you to solve, or those ratios that appear a lot in homework number 1, scaling of our universe. But if you go to the glossary of every single chapter, I will explore the concept associated with them. For instance, gravity. I could have a question associated with gravity. Also, if you download the entire PDF content and then you go to the last chapter, or the last section, I mean, and if you scroll down a little bit more, you have some discussion questions in there. So if you have the time to review them, that would be good. I will take some of these questions that I can create multiple choice, and I will put them in the exam. So no calculations, no math. And this chapter here has lots of physics, so I really don't go there a lot. But if you go to the chapter 2, chapter 2 has good questions. There are more of critical thinking. And how come I'm not getting questions? There you go. So why were 4 of Galileo discoveries, what were 4 of Galileo discoveries that were important to astronomy? And then I can come up with something like that, like Venus phases. And then I can put Venus phases, sun prominences, which is not. So you have to know what they are, right? So I could create questions based on that. So it's, if you ask for a study guide, I would say, well, take your time and read those questions and see if you can come up with something, okay? And if you have questions, always ask me. Good enough? All right. Good night to all of you. Thanks for coming. And I will stop taping now.